Now we'll go over the features you should look for using the Daphne Island example. First, observe the general shape. This histogram is bell-shaped. It's also symmetric, meaning that you could flip the picture around a vertical line at the center and the histogram would look the same. Drawing a symmetry line sometimes helps in deciding how symmetric the data is. By reading the x positions of the leftmost and the rightmost bin, you can estimate the range of the data. I'll guess roughly 6 to 14 millimeters. When I calculate the min and the max directly, I find 5.8 to 13.9 millimeters. I guess I could have made a better estimate by reading off the bin positions more carefully. To estimate the most likely values, I look at which bin positions have the tallest bars. I'm going to estimate that most of the values are between 8.5 millimeters and 11 millimeters. When I actually calculate how many values are in this interval from the data, I find that 81% of the values are in this interval. You should also look for any outliers. Notice that there's one box way out there on the right at just under 14 millimeters. I guess that there were a couple of birds in it, and it turned out to be 2. Just a lucky guess on my part. Finally, by looking at the areas of the bins, you can estimate the median of the data. The median is the vertical dividing line. Half of the shaded area is on the left and half is on the right. I estimated about 9.5. The actual value was about 9.7 millimeters. It's not very easy to estimate the dataset average from the histogram. However, if your data is perfectly symmetric, the two values will be the same. I calculated the mean of the data directly to be 9.6 millimeters, which is pretty close to 9.7, supporting the observation of symmetry. However, be careful with this. Just because the mean and the median are close together doesn't mean the distribution is symmetric. You actually have to look at the histogram for this. There are a number of histogram shapes that you're likely to encounter in real data. The bell-shaped curve is the most familiar. However, in biological and other physical systems, you will often see a long-tailed shape. It looks bell-shaped, but it isn't symmetrical. Rather, it has a long tail in one direction, usually to the right, and the other side it may cut off. Another common shape is decaying. It starts at a certain level and just drops off smoothly without any bumps. Flat shapes are also possible. Bimodal shapes have 2 bumps rather than 1. Sometimes you'll see a bimodal shape when you histogram grades for a course. There were some people who understood the material and some who didn't. We'll talk more about what these shapes tell you in the lesson on distributions and sampling. This video gave general guidelines about interpreting histograms, which we'll summarize here. Start by estimating the standard features. Unusual values or unexpected shapes are starting points for investigation. Use rulers and draw lines to increase accuracy. Histograms with different bin sizes give you different information. It's easier to estimate data ranges using few bins, but a small number of bins may not give an accurate shape. Try different bin sizes to improve your interpretation. And finally, verify your observations by calculation.